In today's lecture, we will introduce one more concept called as static condensation. So don't go by the name. It's a very simple concept and we have been using it in a different form in slope deflection method and the moment distribution method. Let us recall the slope deflection equation. So in general, for a member undergoing angular displacements at the two ends θ1 and θ2, the expression for the bending moment at the left end is 2EIL 2 θ1 plus θ2. So we are very much familiar with this expression. However, if we know that far end is hinge, that is θ2 is dependent on θ1, in that particular case we can reduce the equation to simply m equal to 3IL θ1. So where has θ2 gone? θ2 is now included in θ1 itself and we have suitably modified the expression. This is called as the process of condensation. So don't be misled into thinking that θ2 is 0. θ2 is just included in θ1 itself. θ2 is dependent and θ1 is the master or the independent or the preferred degree of freedom, and once we know the value of θ1, θ2 is already dependent on that. So this is the process of condensation. If we apply it in a multiple degree of freedom system, then we perform the operations in matrix format, and that's what we'll learn today. So what it enables is, it enables us to include the unimportant degrees of freedom into the preferred or the important degrees of freedom. The size of the stiffness matrix can be condensed so that the unimportant or the dependent degrees of freedom, they can be eliminated. So in this manner, the unimportant displacements can be expressed in terms of the important ones. Now this is a very important concept. It has far-reaching practical applications. In this particular course, after a certain lectures, we'll be beginning the most advanced topic, that is the rigid diaphragm action of the floor slabs for lateral load distribution. So in that particular treatment, we have to utilize the process of condensation. Now another application of condensation is in the dynamic analysis. In dynamic analysis, you are already doing your structural dynamics course. So in a given multi-story structure, the lateral degrees of freedom are more important as compared to rotations and vertical displacements. So usually the condensation process helps us to reduce the overall stiffness matrix of the structure into a smaller one in terms of the lateral displacements only. So let's try to understand by this problem. Let's say we have mass at the end of a cantilever and there are three displacements, two translations, one in the horizontal direction u1, other in the vertical direction u2, and third the rotation. Now in such structures, basically u1 is most prominent from the point of view of the dynamic analysis. So we can express the other two displacements in terms of u1. That is, if we know the value of u1, then u2 and u3, they are automatically known. And usually the force applied is generally horizontal. Usually we do not have any component in the vertical direction or the moment component. So that makes the process very simple if we can condense the stiffness matrix. So the stiffness matrix of this structure would be 3 by 3 because there are three displacements, and we do a partitioning like this. So what we have done, we have partitioned deliberately at the interface between the master and the slave degrees of freedom. So u1 is the master degree of freedom here, u2, u3, they are the slave degrees of freedom, or preferred and unimportant degrees of freedom, and generally p2, p3 are 0. That further simplifies our case. Now condensation means that we have to achieve something like this. That is, we modify the stiffness matrix such that we multiply it with the preferred or the important degree of freedom and we get the force vector in the condensed form. So that is 3 by 3 matrix, we are condensing it to 1 by 1. So that's why the term condensation is used, that a larger size matrix is condensed to a smaller size. So what we can do in this particular case, because we have done the partitioning, so we can express these equations in a compact form like this. So K11 is the master degree of freedom, and this matrix K22, K23, K32 and K33 is written as K22 bar. And similarly we have U2 bar. U2 bar is basically inclusive of these two components, U2 and U3. And P2 bar is basically made up of these two forces, and this is usually 0. So now we can express these two equations like this, and somehow if we can eliminate U2 bar from these two equations, we have our purpose achieved. So that's very simple. Just if we can eliminate it by making use of equation number 2. So what we have done, we have expressed U2 in terms of all other parameters, K22 inverse, P2 bar, and in terms of U1. Now if we substitute this equation in equation number 2, we get our desired result. So just by simple arithmetic means, we can write this expression. So here now K11 star is our condensed stiffness matrix. It will be of size 1 by 1, and P1 star is the modified force vector. And in this particular case, because we have P2 and P3 0, so that's why in this particular case P1 star, or the modified force vector, is simply P1. So here we have horizontal translation. This is the preferred degree of freedom, and the rotation and also the vertical displacement, they are the dependent degrees of freedom. So the expression for the condensed stiffness matrix is like this. So what we have done, we have condensed a 3 by 3 matrix into 1 by 1. So important point to be noted is that this does not imply that we are creating any locking at the top. No, locking is not the process of condensation. Here what we are doing, we are including U2 and U3 in terms of U1. We are expressing the other degrees of freedom, the dependent degrees of freedom, in terms of the independent degrees of freedom. So having learned this concept, we will find its very practical application in the next upcoming classes, where we'll study the effect of the floor slab as lateral diaphragm action for lateral load distribution, and that will be especially useful for buildings which are not symmetrical. So thank you very much. Now we introduce another concept, that is the method of substructures. Before formally defining what is a substructure, we will just consider an example. Let's say we have a ring-like structure like this, and this structure is such that the ring is incomplete. Now if we try to find out the bandwidth of the stiffness matrix, and assuming that this is a 3D structure, so we have to do 3D analysis, we'll find that the bandwidth of this particular stiffness matrix, I mean the total structural stiffness matrix, the KPP part, will come out to be 12. Basically here it's the beam which is governing the bandwidth. Now let's introduce a change. We connect the two joints 1 and 7, and we convert this structure from an open ring to a closed ring. In that particular case, now with the addition of a new member, the bandwidth will drastically change. As we have already learned, bandwidth is governed by the largest difference of the degrees of freedom connected by any member. Now here, because we have connected joints 1 and 7, so this member that will be connected between 1 and 7 will govern the bandwidth, and as such the bandwidth will increase now to 42. So this sudden change of bandwidth will lead to a stiffness matrix of this kind. So what we see, that ordinarily the bandwidth is small, but at one junction the bandwidth has suddenly increased. So as a result, when we find out the bandwidth size, we will have a lot of zeros because this particular junction will go on the overall bandwidth adopted finally. So a lot of zeros will be there unnecessarily. So this is one example, and another example is the buildings which have sudden change of the layout. For example, such buildings which have shopping malls in the bottom floors and have office buildings in the upper floors. So here if we see the composition of the KPP, we'll find that the bandwidth suddenly increases to a large number as we go from top to bottom. So in such cases there will be a sudden change of the bandwidth, and as a result the space occupied by KPP will be very large. So in such cases it's better that we break down the structure into two parts such that these two remain separated and we can do analysis individually, and then we can integrate the two analysis. So this is called as the method of substructures. So essentially it helps in solving such kind of structures, like if we have very large ring-like structures, or if we have structures very large and where there is a sudden change of layout, or we have very large structures so that on a small computer it's difficult to analyze. For example, in the finite element software ANSYS, if we are solving a very large structure and if we have chosen a very small and very fine mesh, then the program often runs error that it's unable to create so many nodes and elements. So in such cases we use the method of substructures. So essentially what is substructure? The method of substructures is a computational approach by which instead of solving the entire structure in single attempt, we divide the structure into subparts. So we analyze the multiple subparts individually and then finally we integrate. However, this has to be done such that there is no approximation involved and there is no loss of accuracy in the final results. So it helps us in optimizing, for example, this kind of structure which is very large as well as there is a sudden change of the bandwidth. So we analyze the two individually, so we get smaller bandwidth in the case of the longer structure and we can solve it quickly, and similarly we can solve the other structure because it's now small matrix, it can be solved quickly and then the two can be integrated. So let us see the computational approach involved. Let's say we have an example structure, a ring-like structure, and we have divided into two substructures 1 and 2. So here we define the nodes like this. We have the nodes at the junction which are called as the connected nodes. Here we have shown this kind of sign, but it should not be confused with any kind of fixity. These are just the sections we have cut at this point at these connected nodes, and here we have the forces. The two parts will have internal forces, and these internal forces, they will satisfy equilibrium conditions. So we can draw analogy that just like in the case of a beam, when we try to draw the free body diagrams, we cut the beam into two components, left part and the right part, and if we show the forces at the junction, then perfect equilibrium conditions exist at the cut section. We have the internal forces of the two parts and they satisfy equilibrium conditions. So same applies here too. So we have the two substructures. So C are the common nodes with the internal forces and N are the nodes other than the common nodes. So what now we can do is that for each of the two substructures we can write matrix equations like this. So what we have done is we have grouped all the degrees of freedom, that is all the displacements related to the unconnected joints at one place, and we have numbered the connected joints at the end. Usually the number of connected joints would be very less as compared to the unconnected joints. So as such, the size of UC1 would be very small. Similarly here PC1 are the internal forces at the common nodes, and right now they are unknown. So these are the internal forces at the common nodes and we are not knowing their magnitude at the present stage. Similarly, for the other substructure, we can write equation in the same form. So here, as we have emphasized already, PC1 and PC2, which are the internal forces of the two substructures, they are right now unknown. So here it is also noted that these equations are just like the equations of KPP. So here we assume that Ux is 0. So the equations, they can be simplified like this. Even if Ux is not 0, we can still write the equations in this particular form. Now here definitely the conditions of equilibrium and compatibility are satisfied. Let's review those conditions. Compatibility implies that at the connected nodes, the displacements of the two substructures have to be equal. So this is shown by this equation, UC1 and UC2 both equal to UC. And the other is the equilibrium condition. Because the two parts, they are in equilibrium, so the internal forces at the boundary of the two parts, they will be equal and opposite. So these two conditions, they help us in the solution. Let's now see the solution process. So what we do, that we apply here the method of condensation, and because UC1 is very small as compared to UN1, we condense the system of equations in terms of UC1 and UC2. That's very easy. We just need to write these two equations and then we eliminate simply UN1. Similarly, we write these two equations and we eliminate UN2. So at the end, we'll have compact equations involving UC1 and UC2 as we see in the next slide. So here we have the first equation written like this, and here we have the expression for UN1 and we eliminate it by substituting in the other equation. And once we substitute UN1 here, we get a compact equation like this, where UC1 is nothing but UC that we have seen from the compatibility, and this condensed stiffness matrix KCC1 bar is given by this expression, just like we have already seen how to derive it, and PC1 bar, that is the condensed load vector, is also given by this expression. Similarly, we can write the other set of equations, and here also we can get the corresponding condensed force vector. Now what is common between PC1 bar and PC2 bar? If you look closely, you'll find that here these terms are something related. And second observation is that here these two displacements UC1 and UC2, they are equal. So at best what we can do is that let's add these two equations. So once we add these equations, PC1 and minus PC1, they will cancel out. They are unknown right now, but they will be eliminated from the equations. And similarly, we have UC that will come common. So by solving this system of equations, we'll be able to get UC. And what is UC? UC is basically the set of displacements at the common nodes. So we have solved one part. Then the next thing is that we have to get the other displacement. So one by one, we pick up the equations for the first substructure. Now we already have this part UC1. So now by substitution of this, you can get the other displacements of substructure 1, and similarly you can get the other remaining displacements for the other substructure also. So that way we have solved all the displacements. Now what is left is only the internal forces at the common nodes. They can very easily be solved because now we have the expression for the condensed force vector. This is now known to us. So now we have PC1 bar, which is known to us. So we can solve this equation, and after solving this equation in the expanded form, we can determine what is PC1. And similarly, we can find out what is PC2. So we have solved the entire set of equations. So basically, very large structure has been divided into two components, and each substructure is first individually solved, and then by applying the conditions of compatibility and equilibrium, we are able to integrate the two solutions and get what are the displacements and what are the internal forces at the common points. So thank you very much.